Good morning. That did not need any simulation, guys. Come on. But anyway, my name is Anand Kulkarni. I head the product line and operations at Tata Motors. And it is such a pleasure to connect with everyone in person after such a long gap. Yeah. So, and I must thank Dimple, Ramnik for having organized this, and Sumantra for having made sure that we all assemble, congregate here. So thank you guys. This is indeed a pleasure to interact with all of you and share thoughts, exchange ideas, and nothing like a meeting in person. So on that note, we've done some work in the field of electrification in the past couple of years. I have a few friends in the audience today who have been a part of this journey. Dr. Raja. I want to share with you what our views are, what our thoughts are, and what we've learned in the area of simulation. I'm not an expert either. While I've spent a long time in vehicle development, I'm not the kind of a person who you would say could write down equations and solve complex mathematical situations. But I have a view on how cars get made, how simulations get applied, and where to apply simulations and where to apply engineering judgment. And I hope that what I'm going to speak today adds value, gives you some different perspective into how we've done our work at Tata Motors. Of course, beyond that, if there is anything that we need to talk on, chat up, and if there's anything for me to learn as well, I'm more than happy to do that. So on that note, I want to start off with what Sumantra said, which is a real problem in front of us, that of carbon, or as we like to say from a challenge perspective, decarbonization of the automotive industry. And if you look at what's going to happen between now and the time that most of the companies, most of the countries have announced for net zero scenarios, I would only like you to take back an impression from this that there's a huge amount of work that needs to be done, a huge number of vehicles that have to be converted into, I would not say necessarily electric, but I would definitely say converted into something that do not pollute the atmosphere. And therefore, the entire emphasis on Paris Agreement and us wanting to control the global temperature to within 1.5 degrees of pre-industrial era. The net outcome of this is between 2035 and 2050, automotive industry, transport sector has to go either net zero or at least close to net zero. And if we are looking at new energy vehicles being the biggest contributor, being the biggest lever, I would say, in terms of the transport sector, we should reach 100% penetration. And therefore, if you can imagine that the industry is today at around 150, 170 million vehicles a year, all of this plus the pool that we have has to move to electric is just a very humongous task in front of us. And therefore, the entire portfolio of all these segments of vehicles would need to transition within this timeline, and product development processes would need to shift increasingly and at an unprecedented pace to simulation based, and I'll come to that why to simulation based. But one more graphic on this, and if you see the chart, what I want to say is this is Indian scenario. You look at the total number of models, nameplates that you have versus the volume projection that we have until 2035. The lower portion indicates the number of nameplates. Today we have seven nameplates in a total tally of around 85 nameplates are electric. By 2030, this would have moved to around 32 nameplates out of a possible 125, 130 going to electric. But by 2035, the number of nameplates on electrics will be more as compared to the number of nameplates on ICE vehicles. And therefore, this gives us a unique opportunity. Opportunities are in terms that, of course, as a development fraternity sitting here, multiple products would need to be developed. Therefore, there is going to be automatically more investments in sunrise components, and by sunrise components, I mean motors, power electronics, batteries, etc., rather than investing in fuel injection systems, engines, or gearboxes of the kind that we use today. There is a need for India-specific data to be acquired. Today, this information is not available in the amount that it is expected to be. And the reason why I bring out this India-specific information is because of thermal management becomes a very, very crucial part. I do not have this slide today, but I love to say that most of the EV development in the world that's happened today has happened beyond a certain level. In the 30 degrees up and down of the equator, you do not have too many companies doing electric vehicle development, and that's where the crucial mass of humanity is. And therefore, please look at it as how many products, how many solutions will this belt need to have, and what would be the unique cases that we will have to work on. And of course, the ecosystem is ready to mushroom in our place. Honestly, last 2.5 years, if they have taught us anything, it's about India is more ready for electrification than what we thought at any point of time. So the bottom line is, all of this will move the development budgets of many, many companies from the traditional sunset commodities to sunrise or growth commodities. And that means just a humongous amount of work. How does this imply us? So as I said, emission norms are leading to proliferation of the EV technologies. We need to rapidly develop products. Architecture optimization is going to be a big area. Today we are, at least from a Tata Motors perspective, we took tentative steps in terms of saying we would do conversion products first, and then we would have the Gen 2 and then of course Gen 3. So that's how the architecture optimization is taking place. And of course the end goal is to meet the net zero targets. More importantly, we also have to recognize that at a point when net zero goals are met from a product usage perspective, you would still have the challenge of decarbonizing the EV itself, which means the scope 2 or scope 1 that go into it, the process of manufacturing. So it's all put together, huge implications, bringing out 3 prominent aspects. We need to electrify, we need to go to market faster than ever before, and we need to do this at imperative of reducing product development costs. These are the 3 imperatives that come out very, very starkly. Just as a matter of reference, I've tried to put down here the characteristics of a classical V process, which we are all aware of, versus the characteristics of a closed loop system that all of us are trying to work today in terms of not only design and explore and validate that, but to put in a continuous loop of capturing, monitoring data and trying to analyze and diagnose. So for all this to happen, computability, simulations, making a whole lot of decisions is an extremely important part. And having stayed in the development world for a very long time, I like to say it this way, that development of a vehicle, automotive vehicle, is nothing but acquiring a set of problems and solving one at a time until there is no problem left. And what better way to solve it faster than with the use of simulations, right? So going forward, I want to also lay down a relationship structure that we see today for simulations. And on the vertical axis, I've tried putting down various stages of product development. And on the horizontal axis, I've tried putting down the various components, and you'll see our view of how much, what kind of relationships exist where you can apply these simulations. One important aspect that I would also like to say, and Dimple, this is probably something a little different, but we tend to think of simulations as being applied in an engineering space only, but within the creative space, which is where the product starts, you need to also see what changes are happening. And today, when product timelines, development timelines are shrinking, often the creative process is one that takes a significant lead, a significant time. Because unless your creative process is ready, you can't kick off tools. And then the rest of it is now more or less standardized, right? You send tooling data to the tool maker and it all happens within a time. But how do you hasten, without making mistakes, this entire process of creativity where the designs and everything come together and you have what you need as a product is something that needs to be looked at. And just the last week, I was pleasantly surprised that by using some off-the-shelf software suites like Oculus, for example, our design teams were able to recreate immersive experience of how we would look at cars and how the showroom of the future will look like. And we were all in an empty hall like this, and 4 people in 4 corners, and we were all viewing at the showroom and touching cars. We could not feel it, but we could still touch cars, and you could still make very quantitative but very discrete inputs into how that design should be upgraded, improved, and that's such a empowering feel. So the way that we look at challenges in simulation today, I think a certain aspect exists in terms of a reality gap. And I think that exists in terms of thermal electrochemical models when it comes to batteries. Because no matter how much we try and simulate, you would still find the heat transfers of, for example, in a runaway condition beyond 300 degrees, there are still some challenges about how the separator melts or separates and then causes a short, and how do you therefore use that to run a thermal simulation or thermal runaway simulation. So that's an area that we probably need to work on, and I'm sure Dimple and Ramnik, your teams are sort of scratching their heads on this. The second one is about road load duty cycles, because something has to go in as an assumption into the simulation, and for that matter, the road load duty cycles about how the product is going to be used are extremely critical and crucial, and otherwise you would still have a problem of incorrect assumption leading to incorrect results, crap in, crap out, as they say. So we've got to be careful about that. And of course, material databases make a significant addition to how our simulations can be more accurate. Complexity of simulators is another aspect. Accidental complexity is what I say. You tend to build in more complexity than you actually need to, or you have assumed certain things and then additional things come on, so you need to be careful about that. Not all simulators have all capabilities, definitely not at the cost that you would want to have, and sometimes they are expensive to a point of being outside of reach. So that's another aspect. The continuously improvement cycles, because in the V loop, we saw that it's a linearized way to do things. But in a continuous loop, how do you constantly upgrade yourself with findings that are more latest, more recent, is also something that we need to look at. Remote operations are a current truth. Everybody wants to work from home, and I firmly believe that in a product environment, people all need to be together in order to solve problems. So that's another problem that we are looking at. And of course, supply chain complexities have brought on us the added challenge, I would say, of working with alternatives. And when you work with alternatives, not everything can be a perfect fit. And therefore, we need to look at how we are going to look at these aspects also in order to fix these dynamic situations. I have 3 examples, but before that, I want to sort of lay down simulations at different levels in terms of being fully digital, or where we use prototype plus simulated conditions. In the initial phases, although there are a higher level of assumptions and higher skill requirements, you could still move on very, very rapidly. But as you start to get into the prototype domains, you start to have data which comes in, and at that point of time, models need to get validated and improved so that you can achieve the right level of outcomes. I have 3 examples in terms of a battery simulation. I think I have a powertrain simulation and one on region that we learned. So I'll share that very quickly with you. On the battery front, we're looking at conducting thermal simulations, cell system modeling, mechanical modeling, and electrical integration and simulation. Look at flow, thermal, heat transfer rates, the runaway possibilities, the way in which modules get constructed. A whole lot of that stuff gets done today. But as I said earlier, some part of it is available. A lot of it has to be still done, because in terms of the actual phenomena, electrochemical phenomena and the thermal phenomena that happens when a runaway is taking place, we probably need to improve this a little further. The second example that I would like to share is on finalization of powertrain. So you always start with what your product expectations are, what your product attribute expectations are, and how do you define the key target finalizations, etc., which then help you with simulations in order to give you a broad level feel of whether that particular size is okay or not. And once you've been able to do that, then you do broad motor specifications in terms of power and torque. Then you have the knowledge to understand how much variability or how much control you have in terms of being able to alter the performance. Battery capacities, self-analyzation, and OBC ratings are equal parameters that we look at. What we do today is onboard the suppliers fairly early and run simulations along with the suppliers. So it's moving from the OE doing all the simulations by themselves to a lot of these parts being handed over as systems to our suppliers, so that we are able to leverage on their capability, their usage, and move much faster. Sumantra rightly mentioned about the shortening product life cycles. I mean, our northeastern neighbors have really made an art out of it. Today they develop full-size products within a span of 27 to 32 months, and this is amazing compared to slightly more traditional and Western philosophy, I would say, where everybody was used to 54 months, and now they think they've done a great job by doing it in 40, or aiming for 40 at least, if not doing it in 40. But this is the speed at which we have to catch on, and nothing like helping or getting a helping hand from our suppliers in being able to do that. I would say, and if you looked at what I said in terms of architecture, much as we would like to think that everything about automotive vehicles is known and understood, a skateboard, a kind of a concept for electrification, is still something that not many people have tried. Even the people who have tried, they've done it only for the last 5, 7, 8 years. So a lot of traditional legacy wisdom or data associated with that is not available, and there are significant challenges that one needs to work on. And as I said, a whole lot of ton of decisions to be made. The third example that I want to share with you all is drive factors for regeneration, and the reason why I chose to include this today is because when we were developing the Nexon EV, we thought in our minds as engineers that this is how the customers would want. We want to give a single pedal drive and so forth. And you know what? We had a rude, almost a crash landing, because customers said, "Hey, you guys have done great, but what the hell? I can't control the car." And that's what made us quickly reevaluate what it means in specific drive conditions, in the way that India drives, in the way that traffic happens. And therefore, it's given us a lot of learning. Of course, we ran hundreds of simulations to see if we could use that level of regen for improvement in range, for improvement in drive comfort, for improvement in performance. And this is a snapshot of that outcome. So today we look at not only the battery, motor, and vehicle, which is core elements of how regen can be activated, but more important from a user limitation perspective, driving comfort, the road terrain. You're going upslope, and if you have a very high regen, you're having a double deceleration, and that is extremely difficult to drive. Similarly, you go downslope and you have low regions, you can't control the car to the point that you want. So how do you manage all of these things there could be multiple possibilities, and you don't have the time to do all these things physically, neither is the data very accurate. So that's where we've resorted to simulations in a fair degree. Of course, there are other vehicle strategies in terms of, today's vehicles give us the ability to differentiate on what kind of terrain you are operating, and how do you therefore simulate your region strategies on the basis of that. All of this had to be mapped out significantly. This brings me to a point which is what I call organizational maturity model for simulation. And this is on the basis of what we've learned, what I personally believe over the last 25, 28 years. It's not only about simulation capability. It's also about engineering judgment. And therefore, on a 2x2 simple matrix, you would find that while you could have developing or developed simulation capabilities, you could also have engineering judgments that are poor or strong. And depending on that, you see there could be organizations which want to run simulations but have poor engineering judgment because a past experience does not exist. And the reason why I chose this is because today, within the space of electrification, there are many companies who want to think that it's easy. Getting components from mass manufacturers is easy to bring and integrate. And therefore, some little simulation should be fine, right? But then decision making gets hampered. Early setbacks can cause criticism of the simulation, and result interpretation errors can be expensive. And on the other side, you have some new companies, new startups with youngsters who are great in simulation but do not have the necessary depth of engineering or the experience. So there's a very high belief in simulations, but in the absence of prior database, key issues could be overlooked, and then you could have problems. I think the right way is you could have a path that goes up that way or down that way, because ultimately you want to get into strong engineering judgment and developed simulation capabilities. But I think the message that I want to say is to each of your companies, please invest in growing the engineering judgment along with the simulation capabilities, because they are absolutely complementary, and unless they go hand in hand, being able to grow into a mature organization that knows what it is doing and knows and does decision making in a consistent and correct manner is unlikely to happen. You will have pitfalls with either of these approaches. So that's the way that I think we need to move forward. And therefore, to me, the way forward is, since a massive shift to EVs is happening, decarbonization of EVs and electrification is inevitable. We have fairly little time, relatively less time, and as engineers, we'll all have to make, as I said, a ton of decisions. And of course, simulations will enable us to wade through these issues in the fastest and the best possible manner. And therefore, we have to develop engineering judgment to supplement simulation results. This is what I said in the previous slide. I would suggest adopt a trust but verify approach. They have always yielded results. They will yield results in the future. And India-specific data is not available readily. Therefore, the early movers will have a great advantage, a head start that is very difficult to overcome. And that, ladies and gentlemen, brings me to the end of my discussion with you. Thank you so much for being a patient audience.